we start as we always start. 2 pieces of advice, because they're good pieces of advice. Number 1, do problems, which is why we're here. The more problems you do, the more patterns you pick up, the more patterns you pick up, the more you're able to say, aha, I've seen this before, you can't get me this time. And of course, the second thing, take care of your health, not just your physical health, but your mental health. If you need to, find a good pillow to scream into, no problem, it's all right. It's a judgment-free zone here. And with our advice out of the way, we begin. So, number 1, we're going to start by finding some Laplace transforms of things. So just get in the habit of that. That's going to be an important tool for this upcoming exam. And this exam, more than any other, we want to make sure we have our equation sheet handy. We've been building up all semester with all these things here which weren't really useful until now. So we have all this stuff about Laplace transform, so we want to make sure we have that handy, and we'll probably be pulling that out frequently as we go forward. So part A, the Laplace transform of e to the t sine t plus t cosine t, quantity squared. Okay, well, what do we do? Now you might say, well, maybe I can go look up in my table, and there's pieces there that are right. We got the e to the t, the sine t, the t, no problem. But the square, how do we do that? Well, simple idea, we rewrite. Now, I know this is so obvious, but I just want to write it down because it's important to remember one of your best strategies for working with Laplace transforms is the ability to rewrite your expressions. So for us, our rewrite is going to be squaring. Okay, so we get this as the Laplace transform. Now, if you have a plus b quantity squared, just as a reminder, that's a squared plus 2ab plus b squared. So for us, that means you square that e to the t sine t. There's our a squared plus 2 e to the t sine t, t cosine t, plus t cosine t squared. Okay. And we start chipping away. So this is the Laplace, e to the 2t sine squared t. In the middle we have 2 sine cosine. And we say 2 sine cosine. That sounds familiar. Well, it should. You know, come to your formula sheet, 2 sine cosine. Oh, yep, sine 2t. Ah, nice, nice. Okay, so we have a t e to the t sine 2t in the middle. And we have a t squared cosine squared t on the end. Okay, so we say, are we done with our rewrite? And not quite. Sine we can handle, sine squared, not so much. So we say, all right, well look, if we have a sine squared or a cosine squared, we can rewrite because we have these wonderful identities that lets us reduce the powers. So sine squared can be rewritten and cosine squared can be rewritten. So we plug those in. So we have that this is the Laplace. We have e to the 2t, sine squared is 1 minus cosine 2t over 2. We still have our middle term, which we'll come back to. And then we have a t squared and a 1 plus cosine 2t over 2. Okay, so multiplying it out one more time, we have, this is the Laplace transform, 1/2 e to the 2t minus 1/2 e to the 2t cosine 2t plus, I'm going to suspiciously rewrite the middle term as e to the t times t sine 2t plus 1/2 t squared plus 1/2 t squared cosine of 2t. Now, that's a lot of work, but we haven't done that much surprising. We've applied rules to help us expand, group, gather, rewrite. Rewriting is one of the first steps in taking our Laplace transforms. And now we go through and we sort of say, okay, how do we feel about things? And we say, okay, e to the 2t we like. And as a reminder, when you see e to the 2t, how should you think of that? Well, in general, if you think of e to the at, this is a shift. So it's easy when you have exponentials involved. It's shifting the answer. Not so bad. When you see t, well, oftentimes that's associated with the derivative if you don't have something else already being used for that. So just e to the 2t, no problem. We've got ways to handle that. This e to the 2t cosine 2t, again, we can handle cosine. The e to the 2t tells us there's a shift. Life is good. Now, what about this next term? E to the t times t sine 2t. Well, if we've studied our sheet, we might remember that there is a t sine dt already there. And so now we say, we can handle that. It's just going to be this expression with a shift. So that's straightforward. A half t squared. Well, we know how to handle t to a power. That's straightforward. And then, we saved the best for last. T squared cosine 2t. That's not on our sheet. So how do we handle it? Well, we remember what t means. T means take derivative. Now, you might say, why do you say t means take derivative? Well, if you look, this is our t means take derivative rule. So the Laplace transform of t times something means take a derivative. T squared says take two derivatives, but we'd like to save some work if we can. We're efficient. We want to get from point A to point B as quickly as possible. So we say, well, can I use anything that gets me halfway there? Notice we have a t cosine 2t, or in general bt, ready to go. So I just need to do one more step here. All right, so let's handle the t cosine 2t. We'll do that on the side. So Laplace of just t cosine 2t, I'm just going to go to my equation sheet, and I'm just going to ask you to trust that I'm going to copy this down correctly. Notice here b would be 2, so it'd be s squared minus 4, s squared plus 4 squared. So we have our s squared minus 4 over s squared plus 4 squared. All right, so we have the following. The Laplace of t squared, which is t times t cosine 2t, well, according to our rule, we're going to have a minus, and then the derivative of what we have up above. S squared minus 4 over s squared plus 4 squared. And this is perhaps maybe one of the more challenging things for us to do, is take this derivative today. Well, okay, we'll do it with the quotient rule. So we have minus, we take the bottom, s squared plus 4 squared, times the derivative of the top, 2s, minus the top, s squared minus 4, times the derivative of the bottom. And of course, at moments like this, I realize I did not plan very well. But okay, all right, over the bottom squared. So s squared plus 4 squared squared makes s squared plus 4 to the 4th. You can simplify a little bit, but we're not going to, the goal here isn't for you to simplify all the way. If we don't tell you to simplify, don't panic about simplifying. If we do tell you to simplify, something amazing must happen. All right, now we're ready to write our answer. So we're going to go through and write our answer. Okay, so constants can move out. The nice thing about Laplace transform is it's linear. which means when you have bunches of pieces being added or subtracted, do each piece individually, and constants can come out. So you say, okay, we have a half, that's half, and then the Laplace transform of e to the 2t, according to our table, 1 over s minus 2. Then we have minus a half. Now cosine of 2t on our table would be s over s squared plus 4. But because we're multiplying by the exponential, remember we said exponentials equal shift. So this part that says exponentials equal shift is this piece right here. E to the 2t times something, we're going to replace everywhere we see s becomes now s minus 2. So we would have s minus 2 divided by s minus 2 squared plus 4. Okay, that's the e to the 2t cosine 2t. The e to the t sine 2t, well, again, we already have t sine 2t. We have an expression for it. So we know how to do just the t sine 2t. The e to t means shift. Everywhere we see an s, we now put s minus 1. Here b is 2. So we're going to have plus 2 times 2, which is 4, s minus 1. Downstairs we'd have s squared plus, s minus 1 squared plus 4 squared. Remember, all the s's become s minus 1s. A half t squared, well, we have a half. Then t squared, that's n equals 2, become 2 factorial upstairs over downstairs s to the 2 plus 1, which is s cubed. Plus a half t squared cosine 2t, which is what we worked on over here. And let's see, should we try to maybe even clean that up a little bit? I said we didn't need to clean it up, but now I feel the urge to clean things up. Okay, all right. Minus 2s cubed plus 8s. Then there's going to be a minus 4s cubed. And then there's going to be a 2 times 2 times 2, 2 times 2 times 4, excuse me, plus 16s over s squared plus 4 cubed, which will make this, well, the minus 2s cubed, and I can already see that this is time for people to say, Steve, your parenthesization game is off. That minus goes through everything. And so I only put it on the first term. So this is actually a minus, this is actually a plus, this is actually a minus. Okay, so we'll end up with a 2s cubed minus 24s over s squared plus 4 cubed. Good. And that's it. Okay, this one is challenging just because there's lots of little pieces, but it shows you all the pieces fit together. Okay, any questions? All right, well, this was part A. There's several parts, which now we know why we put this on several pages. All right, I'm still suspicious about that, so I want to just drag my heels for a second here to make sure I didn't do something silly. So that's minus 4. I feel like I've done something silly here. Shouldn't that be a 4 minus 4s cubed and a plus 2s cubed? Oh yeah, that's right. Minus 4 plus 2 does in fact become 2. Okay, all right. We'll speed up, don't worry. Okay, part B. Find the Laplace transform of t, integral 0 to t, e to the 2 times t minus tau, tau cosine 2 tau d tau. All right. Whew. Now this looks challenging. Well, what do we do? Now for this one, we start saying, well, what does this look like? And we have our equation sheet, and we see, there's this piece here. F tau g of t minus tau. This is that star convolution. Great. So we can do something. Now, be careful here. There's really sort of two layers. There's this first piece, which involves that convolution, but then there's this other piece, which I should probably go with a slightly different color, which has a t attached. So I want to just say, and I'll probably get better chances to say this, but look for the layers. A lot of times when we're solving these problems, there's layers involved. And it's just a matter of figuring out how the layers all fit together. It's like we often say, problems are like onions. Onions have layers. And they're also like onions in that there might be some tears involved. But all right. So we start on the innermost level. Say, okay, what's really going on in here? Well, what this is, another way to say this, because we already have it t minus tau, and here is tau, is that this is e to the 2t, and we put this notation here, star, of t cosine 2t. All right. So let's suppose we only had that. Well, according to our rule, if we have that, so we're here, that f star g, that says, okay, if we're just taking the Laplace transform of that, that's not so bad. So what we would do is we would take the Laplace transform of each piece individually. And so this would become Laplace transform of e to the 2t, and the Laplace transform of t cosine 2t. And both of these are on our sheet. So the Laplace transform of e to the 2t, 1 over s minus 2. Laplace transform of t cosine 2t, we actually use that in part A. That's going to be s squared minus, 2 squared, divided by s squared plus 4 squared. Okay, great. Progress. We've dealt with our innermost layer. And now we just have to sort of work through our layers and what they do. Well, we pause for a second and say, could we simplify? This wasn't chosen at random. Something nice does happen here. Does anybody see a nice thing? Yeah, this top can factor to s minus 2, s plus 2, and then we say, whoa, s minus 2's cancel, so it's really s plus 2 over s squared plus 4 squared. Okay. So now that we've done that, we're ready to go to our next layer. The next layer says there's a t times that. We know that when we add that t, what does that mean? Well, it tells us that we have our rule that when we multiply by t, it's taking derivative. So we're going to have that this is going to be equal to minus the derivative of our inner layer. S plus 2, s squared plus 4 squared. I didn't mean us to do two of these back to back, but sometimes that's what happens. Okay, so we'll just do this. Minus, we take the bottom, times rid of the top. I hope you don't walk away saying, oh, he's definitely going to have us do a quotient rule on this exam. No. It just sometimes happens. S squared plus 4 to the 4th. And of course, we could leave it there. We'll clean up just a little bit. We can factor out a single s squared plus 4 and get a little cancellation there. And so I'm going to be careful with my minus this time. That's s squared plus 4. Here we'd have minus 2 times 2s is 4s. And so that's 4s squared minus 8s over s squared plus 4 cubed. And okay, s squared minus 4s squared is minus 2s squared. Don't forget the minus in front, so that becomes a plus 2s squared. Minus minus 8s becomes a plus 8s, and a minus 4 over s squared plus 4 cubed. Okay. All right. So the key here, I would just say, make sure you look for the layers, know how to onionize. Work from the inside out. Okay, any questions? Yes?
Will we have to simplify like that on the exam, or is the first answer?
You don't have to simplify. So if you have an answer that's right, and it doesn't say simplify, then you're good. Life is good. I see another question. Well, I can believe that. Let's see. S squared minus 4. Aha! You didn't notice, but this is actually a badly written 3. So there we go. Good. Good. Problem solved. Yes?
So for, how are you able to get out of doing a product rule between f of s and g of s? If you were to take the derivative of that, wouldn't that be a product rule between those two?
Well, it's not that we're not taking a product rule per se. I mean, in some sense, you could say another way to do this, if you wanted to add layers to our rules, but who wants infinitely many rules? The goal isn't to say write a rule for every occasion. The goal is to say what's a set of rules that lets you solve what you have. So we could say that another way to do this problem, suppose you have t times f star g. Well, then this is the same as minus the derivative with respect to s of fs g of s. That's essentially what we've just done. And so, you asked about product rule, probably want to say quotient rule, but it's hard to avoid. I don't know if this has answered your question at all, but it gives me a chance to ramble.
Yeah, no, I was just confused how we're because right there, wouldn't you have to use a product rule since you're multiplying two functions of that?
Well, so the thing is that when we had our multiplying two functions of s, when we take Laplace transforms, almost always you end up with fractions. All of Laplace transforms inherently have fractions involved. And so when you have derivatives, it's almost inevitable that you have to do something with the quotient rule, unless you're very lucky. All right. Let's move on and do part C, and then we'll be 1/10 of the way done, and only having taken 25% of the time. Okay, part C. The integral from 0 to infinity e to the minus 3t of the integral from 0 to t tau squared e to the 2 tau d tau dt. And you're like, ha! There's no Laplace transforms. This should have been on a Calc 2 exam. Now you could do it in a Calc 2 exam if you had a professor that didn't like you, but you're in differential equations where your professors like you, and we want you to succeed. So what's the punchline here? What does this have to do with anything? Well, remember that the Laplace transform is really an integral. So the Laplace transform of f of t is this integral 0 to infinity of e to the minus st f of t dt. And so oftentimes we get sort of so abstract with what's going on that we forget what it is. And what the Laplace transform is it takes a function and it makes a new function. Now, what you do with that new function, you find out when you take your engineering classes in the next few semesters. But for us, we remember it is a function. So we say, aha, what's going on here is that this looks like the Laplace transform of this integral. 0 to t tau squared e to the 2 tau d tau, right? This is my f of t. And then we evaluate at s equals 3, because we have e to the minus 3t. So the e to the minus st became e to the minus 3t. So what can we do? Well, so we don't actually have to do any integration, which is good. A lot of our work has been saying, let's not do things the hard way. Let's use our tools and do things the smart way. So how do we go about this? Well, first off, again, we have layers. Now you might say, isn't this convolution? No, because there's no t minus tau. It's just straight tau. So what's the rule? Well, in this case, our rule is this one, the integral from 0 to t of f of tau, d tau. And so what that says is you divide what the f would be, divide it by s. It essentially adds another 1 over s. So first off, we start with our inside. So what would be the Laplace transform of t squared e to the 2t? Well, for that, we come to our sheet. We say, well, we know how to take the Laplace transform of t squared, and we know that e to the 2t means shifting. The Laplace transform of t squared would be 2 factorial over s to the 3. Or, well, let's say 2 over s to the 3. So the Laplace transform of t squared, e to the 2t, means that we shift, so we have 2 over s minus 2 cubed. So we use our shifting rule. And now we say, okay, we know how to do our innermost layer. We add the next piece, which is the integral. So what does the integral tell us to do? Well, the integral says add an extra 1 over s. So the Laplace transform of the integral from 0 to t of tau squared e to the 2 tau d tau is 1 over s times 2 over s minus 2 cubed. Okay, we're almost done. We should have started with this one because it's going faster. And it's nice to do things which go fast. What's our last thing we need to do? We need to carry out the evaluation. So we're going to evaluate at s equals 3. So we come to the conclusion that the integral from 0 to infinity, e to the minus 3t, integral 0 to t, tau squared e to the 2 tau, d tau, dt is equal to 1 over 3 times 2 over 3 minus 2 cubed, also known as 2/3. All right. So now we know how to take Laplace transforms of things. If you can do these, you'll be in good shape. Are ready to do the inverse Laplace transform? All right. On to number 2. Find the following. And again, several parts. The inverse Laplace transform, 5s plus 11 over s squared plus 8s plus 25. All right. Well, what should we check as he points towards the denominator? What should we be looking at here? We should look at the denominator. Okay. Now, you should check to see, does it factor? If it doesn't factor, complete the square. Does s squared plus 8s plus 25 factor? We say, try it. No, couldn't do it. Let's try completing the square. So we aren't changing the upstairs. So to complete the square, you say, okay, s squared plus 8s, what would I want to add? Well, divide the 8 by 2, square it. You'd add 16, and then you still have 9 more to go to get up to 25. So this is the inverse Laplace of 5s plus 11 over s plus 4 squared. And I'll write the 9 as 3 squared. Okay. So Do we do partial fractions now? No. No partial fractions on this one, because there's not any pieces to break up downstairs. So when you're doing partial fractions, it's if you have multiplication going on downstairs. We just have one piece. No partial fractions involved. What do we do? Well, we start thinking about it and say, we see that there's an s plus 4 here. Now, we need to make everything look like an s plus 4. So that includes the top. So, say, all right, let's work on that. So that's the inverse Laplace, 5, and I'm just going to make the s be an s plus 4. Now, I'm not done yet, but I start here. 5s plus 4. Now, that would give us a total of 5s plus 20. I need to end up with 5s plus 11. So I say, well, 5s plus 20, I'd subtract 9 to get to 5s plus 11. So you can multiply it out. 5s plus 20 minus 9 is indeed 5s plus 11. And we have an s plus 4 squared plus 3 squared. Okay. Now, this is actually looking pretty good. These look like, very much look like, sines and cosines. So we have b over s squared plus b squared would look like a sine. S over s squared plus b squared would look like a cosine. But you might say, well, wait, what about the s plus 4? Well, that means there was a shift. So whenever there's a shift, our answer in the inverse Laplace will involve an exponential function. So shift on the inside, exponential function at the end. So we're going to break this up into two pieces. We're going to have the s over s squared plus 3 squared. Now I said s, even though I didn't point to s plus 4, but we kind of like squint our eyes and say, well, it's kind of like s over s squared plus 3 squared if we squint our eyes. And so breaking this up, say, okay, look, this is, we'll have 5 times s plus 4 over s plus 4 squared plus 3 squared. That's one piece. And minus something interesting here, okay. S plus 4 squared plus 3 squared. Now, here's what we're going for. When we have our cosine, we just want an s upstairs, so that's fine. When we have our sine, we want to have, if this is our b squared, we want to have a b upstairs. So we want a 3. Since we want it, we'll put it there. See, isn't that great how it works? If you want something, put it there. But you don't stop. You say, okay, how do I make sure everything else balances out? So if I have a 3, what else do I need? I need a 3 out front, because I need to get a total of 9. Okay. So we'll make a few notes here on the sides. So the s plus 4, this means that we're going to gain an e to the minus 4t at the end. Why e to the minus 4t? Because this is s minus minus 4. So it's s minus the number, that's what goes up here. So we're going to gain an e to the minus 4t. And now we say, all right, what do we end up with? Well, so we have the 5. The s plus 4 means e to the minus 4t. And we have that b is 3. So putting that together, we get 5 e to the minus 4t cosine 3t. Then the next term, minus 3. Again, we're going to have that the b is 3. We have a sine of 3t, but because of that s plus 4, we're going to add an extra e to the minus 4t, which caused the shift. And that's the answer. All right. Any questions here? Okay, on to part B. The inverse Laplace, 3s minus 7 over s squared times s plus 1 times s squared plus 1. Okay, I'm going to preface this by saying, well, we know where we're going, partial fractions. But I'm going to add, this partial fractions is way more than what we'd asked you on an exam. But we always do the hard ones for practice. So on the exam, we're going to be like, this wasn't so bad. It could have been worse. Okay, well, all right, I already gave it away. It's partial fractions. And so we begin. So we have our 3s minus 7, s squared, s plus 1, s squared plus 1. Okay, how many pieces will we have on the other side? 2, 3, 4, 7, 4. 4 is right. All right, so what do we have? We have s squared, so we build ourselves up. s squared. We have a single s plus 1, and then we have an s squared plus 1. Upstairs, we're going to have a constant, another constant, and a d times s plus e. Now, this is usually the point where people say, why did you put a ds plus e here, but not there? And the answer is, look at the downstairs. It's not so much the square, it's the fact that what you're squaring. You're squaring something that's linear. Here, the square is involved in something which is quadratic, which can't be further reduced. It comes down to how far can you reduce. And all right, good. So we just have 5 unknowns. All right. So the method, you set it up, and then clear your denominator. 3s minus 7 would be equal to a times s plus 1 times s squared plus 1 plus b times s plus 1 plus c times, oops, I forgot to add some terms. I was so excited. Okay, so plus b times s plus 1 times s squared plus 1 plus c times s squared plus 1 plus d times s plus e times s squared times s plus 1. All right, good. Well, what should we do? Yeah, we can make some good choices. Someone suggested plug in -1. All right. If we plug in -1, 3 times minus 1 is minus 3, minus 7 is minus 10. And then we get 0 and 0. On the end we get 0. So we get c times 1 times 2. So 2c equals minus 10. c equals -5. Okay, that wasn't hard. Anything else we can do that's easy? Plug in 0. All right, plug in 0. So, what do we get? 0 minus 7 is -7, is 0, plus b times 1 times 1, which is 1, and 0 and 0. Ah, great. B is -7. Wonderful. Okay. Now what? We've got 2 things figured out. Now, I could show you something that's fun, which you probably have never been taught, just because it's fun. You know the ideas. We can do a little shortcut. Or we can brace ourselves. What? Oh, good. An imaginary number. This is going to be fun. All right, here we go. Which imaginary number shall we plug in? I. I's the number. Okay, so we plug in I. We're going to get 3I minus 7. I know, hold on. In the first piece, what happens? 0. In the second piece, 0. In the third piece, 0. And then something. Okay, so that's D times I plus E times minus 1 times 1 plus I. Now, you might be a little skeptical here to feel like, I don't think we've learned a lot, Steve. But wait, there's more. Let's expand this right-hand side. Okay, so let's see, we'd have a D times I, don't forget the minus, so that's a minus DI, then a DI squared, so minus D, don't forget the minus though, so that makes a plus D. And then we have E times minus 1 times I, which is a minus E, and E times minus 1 times I, which is a minus E times I. Okay, so which becomes, well, D minus E, this part here, plus minus D minus E times I. All right, so are you ready for the cool fact? Which will make things like, whoa, that's so cool, I love it. All right, here we go. You don't need to know this, but this is, I'm just going to save myself some time. D and E, whenever you're doing partial fractions, and you're starting with everything is real, all these coefficients are real. Which means that D minus E is a real number, and minus D minus E is a real number. Now, why is that useful? Well, it's useful because if I have two imaginary numbers equal to each other, then I have to have that the real parts are equal, so that this D minus E is negative 7, and the imaginary parts are equal, so that minus D minus E is negative 3. So we now know that D minus E is negative 7, and if we just multiply everything through by negative, D plus E is 3. Well, can we use that to solve for D and E? Yes. Let's add. What do you get? (2D) is equal to negative 4. So what is D? Negative 2. All right. So negative 2 plus E is positive 3. So what is E? E is 5. I see lots of questions here. Did I not get this right? Ah! You're right. Well, that's okay. That's why we have whiteout. Wait, I forgot my whiteout. Okay, so we just do this again, and we add, same process. 2D is negative 10, D is negative 5. Once we know that, negative 5 plus E is negative 3, so E is positive 2. All right, once I know how to copy things. All right, good? Are we done? No. What have we found? We found B and C and D and E. What haven't we found? Oh yeah. Oh yeah, eh? Oh sure. You betcha, eh? Okay. How do we get that A, eh? What do we plug in? You plug in any number you like, because we already know all the other ones. And so if we plug in one last number to get the ones we want, life is good. So do you have a number that's easy to work with? 1. Good. You've chosen the right one. Okay, so plug in 1. 3 minus 7, negative 4, is equal to a times 1 times 2 times 2. That's 4a, which we don't know, plus b. But wait, we know b is negative 7. So negative 7 times 2 times 2, negative 7 times 4, plus c, which is negative 5, times 1 times 2. So that's times 2. Then we have d times 1. Okay, so, well, d times 1 plus e, so that's d plus e. We actually know what d plus e is. It's negative 3. And then times 1 times 2, which is times 2 again. Okay, so that becomes 4a minus 28 minus 10 minus 6. Very negative there, but that's all right. That would be minus 44. Add 44 to both sides. 4a is equal to 40. So a is equal to 10. All right. So all of this is to say, we haven't done anything with the inverse Laplace yet. The whole thing here is that partial fractions is helping us pull things apart. That's what partial fractions was built for, pulling things apart. So the original problem, Laplace inverse of what we started with, is equal to the Laplace inverse of, we have 10 times 1 over s. And then we're going to have our b, negative 7, 1 over s squared. Then we're going to have our c, which is negative 5, 1 over s plus 1. And the ds plus e, well, I'm going to separate that out. So the d, which we said was negative 5, so minus 5, s over s squared plus 1. And then the e is 2, so plus 2, 1 over s squared plus 1. Okay. And even though we don't have much space left, we don't need much space. 1 over s, the inverse Laplace for that, is 1. So we get, a 10. 1 over s squared. Well, that would be taking our Laplace transform of t to the n and using n equals 1. So that would be 1 over, 1 factorial is 1 over s squared. So that means that this becomes a minus 7 times t. Then we have a minus 5, 1 over s plus 1. That becomes an exponential plus 1. That's s minus minus 1. So that's going to become an e to the minus t. S over s squared plus 1. That's our cosine with b equals 1. So minus 5 cosine t. And then plus 2. The 1 over s squared plus 1 is our sine with b equals 1. So plus 2 sine t. And there we go. Whew. Done. Done. All right. Like I said, this will be certainly more challenging than what you'd expect to see on an exam. I see a hand, yes? So from here to here? Yes. Right. So don't worry so much about the constants. Focus on the pieces. The 1 over s, the 1 over s squared, the 1 over s plus 1, s over s squared plus 1, and 1 over s squared plus 1. So 1 over s is on our chart. So that became a 1. 1 over s squared follows into this category where we set n equals 1. So we see 1 factorial over s squared. So 1 over s squared would be a t. So that's our next piece. The 1 over s plus 1 follows this rule. So s plus 1 is s minus minus 1. So that would be e to the minus t. Now we're to s over s squared plus 1, and that's here. S over s squared plus 1 would be cosine t. So that's this piece. And then 1 over s squared plus 1 is here. So that's where we get the sine t. Is A 11? I don't know. Well, let's see. This would be minus 38, which would be minus 44. And then we add 44. 44 subtract 4 would be 40. And then divide by 4, which should give us 10. I see a hand way in the back. So I'm sorry, can you say it one more time?
Why is the S under the first step? Yeah. Why is that there when it's not there?
So why is it here but not where?
The original problem before that.
Well, it is in the original problem. So you're probably saying, we had this s squared, right? So we didn't have an s times s squared, we just had s squared. Whenever you have something to a power, you've got to climb the ladder. So it's not just right jump to the top of s squared, you have to have the intermediate step s and s squared. So if we had s cubed, we'd have to have an s and an s squared and an s cubed. Now secretly, don't tell people I said this, secretly what's going on is these two pieces here, what it really is the following. It has the form as plus b over s squared. It's a little bit easier to see here. We don't say that out loud because we don't want to confuse you. But now, if you pull it apart, you had as over s squared, you get the a over s, and then you'd have the b over s squared. So that's why this happens, is that what actually should happen is this should be your expression, but then we pull it apart. Then if you end up with a cubic in the denominator, you did something to your instructor and they're not happy. No. If you end up with a cubic, it would factor. We are nice people. We're not going to make you have to factor a cubic. So it's already going to be factored for you. All right. So there is a part C, which looks intimidating when you first see it. And because you look at your table and you say, there's nothing there with the log, and there's a log here. The inverse Laplace log of the square root s squared plus 1 over s plus 1 squared. Now, what does this have to do with our table? Well, we start searching and say, is there any hope at all? And there is actually some hope. And it comes right here. And it says, well, this part says you can take a derivative. And the nice thing is that log, you can take derivatives and they become nice. Logs disappear. So let's talk about this rule. So we want to get to the point where we're comfortable. So I'm just going to use a single t. T f of t is equal to minus, I'll just simplify it by saying f prime of s. All right. So what do we get? Well, you could say this is the same as saying t f of t is equal to minus the inverse Laplace of f prime of s. Now, every single rule that is on the sheet actually is two rules. One rule is using the Laplace, but there's another rule that says the inverse Laplace. And you could even go one step further. So secretly there's, again, I don't want to fill up our equation sheet with rules. It's just a matter of playing with things. We can say that f of t is minus 1 over t, the inverse Laplace of f prime of s. Now why is this nice? Well, what is f of t? It's the inverse Laplace of f of s. So it says, if I have something I can't do for the inverse Laplace, but I can do its derivative, then life is good. So instead of doing the original problem, take the derivative, then take the inverse Laplace, and then add a minus 1 over t. So it's this basic rule. It's just learning how to use your rules. And that's where we want to get to. You might not get to it 100% in this class, but you will. You'll see Laplace and inverse Laplace sometime in the future. Somebody in your major said, this is an important class, an important topic. We want you to see it. All right. So here, this is our capital F of s. So we're going to start by finding the derivative. Now, before we take a derivative of a log, what should we do? We should simplify. Logs are built to simplify. That's why we wanted to study logs. So log of the square root s squared plus 1 over s plus 1 squared. We're not doing any derivatives here. We're just pulling it apart. The square root can come down as a half. We'll just do that at first. So you have an s squared plus 1, s plus 1 squared. But now division becomes subtraction. So 1/2 log of s squared plus 1 minus log of s plus 1 squared. And so this would be multiplying in 1/2 log of s squared plus 1. We can again bring the 2 down. A half times 2 cancels. So minus log of s plus 1. Okay, so this again is our f of s. We now find our f prime of s. Okay, so we've separated out as far as we can with logs. Take the derivative of log. We take 1 over the inside times the derivative of the inside. Do that again. 1 over the inside times the derivative of the inside. So that the first piece becomes s over s squared plus 1. The second piece becomes 1 over s plus 1. Can we take the inverse Laplace here? Well, so we're asking, can we take the inverse Laplace of s over s squared plus 1 minus 1 over s plus 1? We start scanning our table. Do we have anything that looks like s over s squared plus 1? Yes. That's the cosine function. So we get a cosine of t. How about s plus 1 downstairs? Well, that's our exponential function shifted, right? S plus 1 is s minus minus 1. So this is going to become a minus e to the minus t. Now, is this our answer? Well, almost. We just need to add one more piece. Multiply by a minus and divide by a t. So we get that our Laplace inverse of f of s is minus 1 over t, what we just found. And multiplying the minus through, we just flip the order. E to the minus t, subtract cosine t over t. Part C's have been the easiest ones. We should just make all the tests part C's. Right? In case you're wondering, is there any problem that involves a part C on the exam? The answer is not anymore.
How did we go from
Well, so this 2 upstairs, exponents come down in front. So there's really a 2 now in the front, but there's also this half multiplying in, and so 2 times a half becomes just the 1. So, all right. Well, now that we've got these problems out of the way, we can get to some fun stuff. Number 3. No parts A or B, just the number. This is great. Rewrite the initial value differential equation tx double prime plus t squared plus 1x equals square root of t e to the 2t with x of 0 equals 2 and x prime of 0 equals minus 1 as a differential equation in terms of x of s, where x of s is the Laplace transform of x of t. So what's happening here? It sounds complicated, but really what's happening is the following. We're going to take our original equation and we're just going to take the Laplace transform of both sides. So tx double prime. Now here I'm going to find it convenient to multiply. So t squared x plus x. And that's going to be the Laplace transform of square root of t. I'll write that as t to the 1/2 e to the 2t. So we're going to go through term by term and figure out what happens. All right. So we have, expanding a little bit more, t x double prime plus the Laplace transform of t squared x plus the Laplace transform of x. Okay. T to the 1/2 e to the 2t. We'll start with the first term. Now, x double prime. Very important lines near the bottom. We know how to take the Laplace transform of x double prime and x prime. Very rarely, I can't remember a time when we actually asked you to do a higher derivative, but we could. So we're going to make sure we know how to do these. Okay, so double prime would just say what? Well, again, think of this as your onion. You've got your x double prime, and then you've got the t that's doing something to it. So let's start with the x double prime. So the x double prime would be s squared capital X of s minus s times x of 0 minus x prime of 0. Okay, so that's the x double prime. What does the times by t do? Times by t says take derivative. So we want minus this derivative. Okay, that's the first piece. Now we come to our next piece. T squared x. Well, look, we know how to take the Laplace transform of x. It's just x. That's all it is. But what does the t squared tell us to do? T squared, we find it on our sheet somewhere, tells us to do 2 derivatives. And minus 1 to the 2 says we're going to add 2 derivatives. Oops. ds squared. All right, Laplace transform of x is, well, just x. That's not so bad. Equals. Now we come to the other side. Okay, so the e to the 2t is a shift. So focus on t to the 1/2. Is that on our table? Well, yeah. We can handle t to any power. If it's a whole number, we use our rule for factorials. If it's not a whole number, then we come and we use this rule here. So, do a little bit of work on the side. We have that just the Laplace transform according to this rule of t to the 1/2 would be gamma of 1/2 plus 1, which is 3/2, over s to the 3/2. Now, can we do anything with the gamma? Well, yeah, we can. So gamma of 3/2, which is really a half plus 1. According to this rule, that's a half gamma of a half. Well, what's gamma of a half? It's square root of pi. Okay, so updating, we have that the Laplace transform of just t to the 1/2 is this fun constant square root of pi over 2 times 1 over s to the 3/2. Now we add in our shift. So we're doing e to the 2t. So the Laplace transform of t to the 1/2 e to the 2t, well, if we multiply e to the 2t, we put everything in terms of s minus 2. So that's square root of pi over 2, 1 over s minus 2 to the 3/2. Okay, so that's this right-hand side, square root of pi over 2, 1 over s minus 2 to the 3/2. All right, well, we can do some quick updates here. Do we know what x prime of 0 is? Yes, because they told us. So this minus x prime of 0 is going to become a plus 1, minus minus 1. Do we know what x of 0 is? Yes. So this will become a minus 2s plus 1. Now we take our derivatives. So how do you take the derivative of s squared times x of s? Product rule. So there's a minus sign. Derivative of the first, 2s, times the second, plus the first, s squared, times the derivative of the second, x prime of s. What's the derivative of minus 2s with respect to s? Minus 2. Derivative of 1 with respect to s? 0. The second derivative. Well, that's easy. The second derivative. X of s, don't need to do anything there. And we have our right-hand side. Square root of pi over 2, 1 over s minus 2 to the 3/2. And now we'll just write things as we normally would. We start with the highest order derivative. So we have an x double prime of s. That takes care of this piece. There is a single x prime. Okay, don't forget the minus. So minus s squared x prime of s. For the x of s, there's 2 of them. So if we put those together, there's 1 here. There's a minus 2s there. So we can write this as 1 minus 2s x of s. And this last minus 2, that doesn't depend on x of s. We normally would move it to the other side, so we'll do it here. So we have the square root of pi over 2, 1 over s minus 2 to the 3/2. And this will come across, because there's a minus, it'll come across as minus 2. Now, what do we do next? Sorry, I went kind of quick there, but what's the next step? Yeah, we're done. Because we were asked to rewrite it. We weren't asked to solve it, which is good, because we can't. It's outside of what we can do. But we were just saying, hey, we can take a differential equation and transform it into a new differential equation. So we have the ability. And that will happen if you ever see t showing up in front of our pieces. All right, good. Any questions? No? All right. Well, on to our next one. Number 4. Find the Laplace transform of the absolute value of 1 minus t e to the t. Okay, so looking at this, we say there's nothing here with absolute value. But we say, hold on, how do we think of absolute value? piecewise. So the key idea here is that this is a piecewise function. So whenever we have piecewise functions, and we do here, we're going to step in with our u. This is our unit step function. But really, I like to think of it not as the unit step function. I like to think of it as our on-off switch. And in particular, we have this really important rule. It's so important, it got aligned to itself. Actually, it's just very long, so we couldn't fit anything else on the line when we put it in there. So whenever we have piecewise functions, when we do the Laplace transform, it introduces exponentials. So we're going to end up with some exponential on the other side. And so we say, okay, well, first off, we have to understand. Where does the absolute value of 1 minus t change behavior? Because we're thinking of it as piecewise, so it must be changing behavior somewhere. Where does it change? Yeah, when the inside equals 0. So when does the inside of one absolute value 1 minus t equal 0? Well, the answer is when 1 minus t equals 0, which is t equals 1. So before 1, the absolute value doesn't really do anything because 1 minus t is a positive expression. After 1, it flips the sign. So this is for t less than 1. This is t greater than 1. It doesn't really matter which one is less than or equal, greater than or equal. They can both be the same. All right. So now we say, okay, our function, so we're going to let f of t be our 1 minus t absolute value times e to the t. We want to rewrite it in terms of the unit step function. So we say, all right, what do we start with? We start with this 1 minus t e to the t, and then we change behavior at 1. So since we change behavior at 1, we put an on-off switch at 1. So this is our introducing our on-off switch. And now we turn on what happens after 1. So minus 1 minus t e to the t. Subtract what came before 1. We're turning off what was before. So turn on what happens after, turn off what came before. And then that's it, because we only have one place where we change behavior. So we keep cleaning up here. Now, in this first part, I'm going to go ahead and just expand this as e to the t subtract t e to the t plus u of t minus 1. Well, I can see I have a minus and a minus, and so I can put these together. It's like I have minus 2 of them. But I can really say, look, minus 1 minus t is the same as t minus 1. So I can say this is 2 times t minus 1 e to the t. Now we come to our rule that we have here. When we have this unit step function, it's critical that this function matches on the inside. So if I have t minus 1, I need to have t minus 1. Okay, so we start looking here and say, does this look like t minus 1? Well, that looks like a t minus 1 because it is, but there's a t there which doesn't. So how do we fix that? And we have to fix it, by the way. Well, the answer is you add and subtract 1. So it's t minus 1 plus 1. Right? If I need to make something look like t minus a, I can say I'll make it look like t minus a, but then I have to compensate. So in this case, I add a minus 1, then I put a plus 1 right away. Now the nice thing is, I can separate this as e to the power t minus 1, e to the 1. So this can become e to the t minus t e to the t in the front. The 2 is a constant. I have an e to the 1. So that becomes 2e u of t minus 1 times t minus 1 e to the t minus 1. Okay. All right. We're ready. We're ready. So here we go. Any questions of getting to here? This is the hard part.
Like factor out e to the t, but just use it as a shifting factor?
So why can't we factor out e to the t and use it as a shifting factor? That is a great question. And part of it comes down to, you have to be a little bit careful about what happens with this unit step function. Because the shifting factor, it will become a shifting factor, but you have to account for it. If we just pull out e to t, we wouldn't be able to get this e to work. So you have to be slightly careful. Okay, so here we go. The Laplace, e to the t minus t e to the t plus this other stuff, u of t minus 1. And I'll add some extra parentheses here, because who doesn't like an extra round of parentheses? Okay, so piece by piece. E to the t, we can handle that. There's a rule. So that would be 1 over s minus 1. T e to the t. We know how to do t. So there's a rule. T to the 1 is 1 over s squared. The e to the t then says to shift it. So instead of being 1 over s squared, it'd be 1 over s minus 1 squared. So the e to the t is where that s minus 1 is coming from. Then we have our plus 2e. And now we pause, say, well, this part right here is our f of t minus 1. Because we want u of t minus 1, f of t minus 1. So our f of t would be t e to the t. Just imagine everywhere you see a t minus 1, rewrite it with t e to the t. And this would go to what? Well, it would go to 1 over s squared. T e to the t would go to 1 over, it would go to 1 over s minus 1 squared. How do we know that? Because we did it right there. Okay, so what comes here? Well, the punchline is you take that transform of f of t, that's what this f of s is, and you multiply it by an extra piece. So it's going to be e to the minus, here a is 1, so it's e to the minus s times 1 over s minus 1 squared. And now that I look at it, you probably could have just pulled out an e to the t and done that later. But it was good to practice. All right. Well, this is part A. So we have a part B coming. Part B. Find the Laplace transform where f of t is a piecewise function. All right, so we have, it looks like two pieces, or is it? What? Okay, so it's 4 between 2 and 4, and it's 4t minus t squared otherwise. Well, okay, so piecewise, again, we're thinking about our unit step function. All right, well, for this, we say, what do we need to do? Well, let's talk about how we start. How do we start? And when I say start, we start at 0. Do we start as 4 or 4t minus t squared? Yeah, we actually start as 4t minus t squared. So our f of t, we need to rewrite it using our unit step function. Where do we change behavior? We change behavior at 2. So we have u of t minus 2. Our behavior after 2, we flipped, so it's now 4. So we're turning on the 4, subtract, turning off the 4t minus t squared. Where's the next time we change behavior? Well, at 4. And now we do the opposite. So we're turning on the 4t minus t squared, because we're going back to that, turning off the 4. Okay, so we have 4t minus t squared at the start. U of t minus 2. Well, this becomes t squared minus 4t plus 4. And here we have u of t minus 4. And we're going to get minus t squared plus 4t minus 4. One of these two is nice. The other one is going to be, Which one of these two is nice? What's another way to say t squared minus 4t plus 4? T minus 2 squared. Now why is that nice? Because it matches. U t minus 2, t minus 2 squared. Ah, wonderful. Our favorite thing. It's matching. Matching is good. Matching is wonderful. Does it match here? Well, no, because it turns out, it's minus t minus 2 squared. And t minus 4 and t minus 2 are not the same. So we're happy here. We're a little sad over here. All right. Well, we don't need to do much here. What do we do here then? Well, we do our same trick, right? I need to make it look like t minus 4, so I'm going to. So I'm just going to go through each piece. Say, look, this t squared is really t minus 4 plus 4 squared. This 4t becomes really 4 times t minus 4 plus 4. And then I have a minus 4. So when it doesn't match, that's sad. We have to somehow work it out. It means more work. Well, we're not that nervous about more work. I hope not. Okay, so this becomes minus t minus 4 squared. Then we'll have our cross terms, 8 t minus 4 and 16. Then we'll have plus 4 t minus 4 plus 16 and a minus 4 on the end. And so let's see, what is that? Minus t minus 4 squared. There's a minus 8 and a plus 4, which makes this minus 4 times t minus 4. Minus 16 plus 16 minus 4 makes a minus 4. So you have to rewrite it. So what do we have? We have that our function is 4t minus t squared u of t minus 2 times t minus 2 squared u of t minus 4 times minus t minus 4 squared, subtract 4 times t minus 4, subtract 4. All right. So that's our function. Good. Now that you've rewritten your piecewise function, we take the Laplace. A lot of the work, most of the work, is in learning to rewrite. I guess the other part, that's most of the work, is learning to use your table. So, piece by piece. So Laplace of 4t minus t squared, u of t minus 2, t minus 2 squared, u of t minus 4, minus t minus 4 squared, subtract 4, t minus 4, subtract 4. Lots of rewriting. Okay, do we know 4 times t? Well, yeah. We've talked about t before. T to the 1 factorial over s squared. So we have 4 over s squared. T squared. We have the Laplace of t squared, 2 factorial over s to the 2 plus 1. So that would be 2 over s cubed. Now, u of t minus 2 times t minus 2 squared, remember our rule. We have our function has been written in terms of t minus a, so we're really thinking our underlying function would just be a normal t squared. I just want to take t squared to get that f of s. We've took t squared, that's 2 over s cubed. So what we'll end up with is we'll have a plus 2 over s cubed. So that's this piece. And then we add an e to the minus 2s. That's coming from the u of t minus 2. So 2 over s cubed, e to the minus 2s. And we come to the end here. So, all right, the function that's underlying this is minus s squared minus 4s minus 4. So we just go through and we take the transform of that. Well, the minus, oh, sorry, I put s to this there. It should be t's. There's a t squared and a 4t. The t squared, we know how to do that. 2 over s cubed. So we have a minus 2 over s cubed. 4 over t. Well, we know how to do that. That's going to become a minus 4 over s squared. Minus 4 is minus 4 over s. And then that u of t minus 4 is e to the minus 4s. And we found our Laplace transform. So we're done. Whew. All right. Good. Any questions? Yes, I want.
Can you run that through how and why we had to change the fixed up with negative t minus 2 squared? The front face.
From here to here?
No, with the frowny face.
Sorry, where?
With the frowny face, the happy face.
So how did this become this, or why is this happy and this is that?
Why we had to change up the negative one?
Well, all of this had to change because we have to make this in terms of t minus 4. That's why we're unhappy here. Because the t minus 2's match, we're happy here. So you want things to match. Matching is good. So look for the matching. Be happy if you get it. Okay. I think that's our last problem, which has multiple parts. For the rest of it, we're going to fly. All right. Relatively speaking. Number 5. Give a sketch for the function, the inverse Laplace of 8 minus 9 e to the minus s minus 3 e to the minus 5s plus 4 e to the minus 6s all over 2s squared. Before we start, do we know certain things? Is this going to be a piecewise function? Yes or no? Yes. How do we know it's going to be a piecewise function? We see things that involve the exponential function in terms of s. If you see exponential pieces in terms of s, it is piecewise. Do we know where we're going to be changing e to the minus s would correspond with the change of behavior at what point?
1.
At 1. So there's going to be some behavior before 1, some behavior after 1. Where's our next change going to occur at? At 5, e to the minus 5s. There's going to be some change happening at 5. And finally, there's going to be some change happening at 6. So we have a piecewise function. We're going to have 4 different pieces. From 0 to 1, 1 to 5, 5 to 6, and then after 6. Now, the nice thing is we say, hey, these are all very similar. So we can write this as the inverse Laplace. We'll do the first thing, 8 over 2. Well, that's 4, 1 over s squared. And then we're going to have minus the inverse Laplace of 9 over 2, 1 over s squared e to the minus s, minus 3 over 2, and then it's going to be e to the 1 over s squared e to the minus 5s, and then finally a plus 4 over 2, which is 2, of 1 over s squared, 1 over s squared, e to the minus 6s. I didn't quite make it, but okay, you can pretend like I did. We come to our formula. We have e to the minus as f of s. So in our case, our f of s is always 1 over s squared. It's always the same thing. And there's just different constants. Okay, so what is the inverse Laplace of 1 over s squared? Well, we come up here. That would correspond to putting n equals 1 in this relationship. So the inverse Laplace is t. So what are we going to have? Well, we're going to have our f of t minus a is t minus a. And then we just have to know where to switch things on and off. So initially, we have 4t, just this inverse Laplace here. Then minus the 9/2. We switch at 1. So we're going to have a u of t minus 1. And then we're going to times that by t minus 1. Right? Because that's our f of t minus a. Minus 3/2. Our switch comes at 5. U to the t minus, u of t minus 5 times t minus 5 plus 2 u of t minus 6 t minus 6. Any questions on what we did? I know I'm going a little bit faster than I did at the beginning, but I figure we can speed up a little bit. Okay, are we done? No. What do? Well, we have to sketch it. So we say, okay, what's the behavior before 1? Well, before 1, nothing has turned on except for this first piece. So our behavior is 4t. Well, that just says I start at 0. I have a slope of 4, so I'm going to go like that. Good news is I know how to draw straight lines. Now, between 1 and 5, we've added a new on. These haven't turned on yet, but this one has. So we'll update what we have. 0 less than or t less than or equal to 1. We're at 4t. 1 to 5. We're going to be at 4t. Subtract 9/2 t minus 1. Okay, well, we can be a little bit careful here. So 8t minus 9/2 t will end up being minus 1/2 t. And that'll be a plus 9/2. Well, at t equals 1, we'll still be at 4. What's our slope now? Our slope is -1/2. So we're going to go, wait, what? Nope, nope. That's -1/4. I know how to draw -1/2. There we go. Ha 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 ha. -1/2. Okay, so this is our -1/2 t plus 9/2. All right, now we go to our next switch. So that says we haven't turned on the 6, we have turned on the 5. So 5 to 6. We still have the 4t. We still have the -9/2 t minus 1. Now we have a -3/2 t minus 5. Well, we know the first two terms become -1/2 t plus 9/2. And we have a -3/2 t and a plus 15/2. Well, -1/2 minus 3/2 is -2t, and 9/2 plus 15/2 is 24/2, which would make it a plus 12. But at 5, we still are here. What's our new slope? -2. So that's our next piece, -2t plus 12. And finally, we get our last part. 6 less than or equal to t less than infinity. Everything's been turned on. So we have all our switches are on. And so we add 2 times t minus 6. But we say, well, look, we know that the previous part was -2t plus 12. We're adding 2t minus 12. The net result is 0. So the last stretch is 0. So it goes up, down, steep down, back to the axis, and flat. So that's our sketch for our function.
Which side of each jump is inclusive? Like, is the heavy side?
Yeah, I'm being a little bit lazy here because I know that everything's going to line up. Here's the thing. Don't worry about that point. So when we take Laplace transforms, we don't care what happens at a single point as long as delta is not involved. If delta gets involved, okay, that's a different story. We sort of gather around the campfire and sing songs about delta. But otherwise, don't worry about endpoints. Round 2. We're halfway through. But the second half goes a lot faster. It goes a lot faster. All right. So a 40-gallon tank is initially full of pure water. So we've got to draw our tank. We have our 40 gallons. It's full. At time t equals 0, brine starts coming in to the tank at 10 gallons per minute. And there's a concentration of 2 ounces of salt per gallon. Okay, at the same time, the well-mixed contents of the tank are being emptied at 10 gallons per minute. So the nice thing is the amount in equals the amount out. The water level does not change. Very convenient. So far, nothing very surprising. After 5 minutes, the concentration of the brine coming in switches to 1 ounce of salt per gallon. So this 2 ounces per gallon actually only holds for the first 5 minutes. And then it goes to 1 ounce. So something changes behavior. So 5 less than t, and it looks like there's no other restrictions. set up and solve using Laplace transforms a differential equation for the amount of salt in the tank at time t. Okay. So, well, we'll use, let's set x of t equal the amount of salt. Then what do we have? X prime is the in minus the out. That's not too surprising. So for us, what happens? Well, our inflow, it changes. For the first 5 minutes, it's 20 ounces coming in, 10 times 2, the rate times the concentration. Then after 5 minutes, it becomes 10. Now, how do we capture that? And I really want to have sort of a quick question, mini sidebar. When we see this, there's often a question of what are we having here? Is this a U or a delta thing going on? So for us, is this a U or a delta situation? This is a U situation. So U situation is a change in behavior that's sustained. What's a delta situation? A delta situation is a one-time like pulse. So like a delta situation in terms of brine, somebody came and dumped a big, 5-pound thing of salt into the tank. That would be a delta situation where it's just that one instantaneous moment that something gets affected. Sustained, that's a U, that says we're switching behavior. So what is the behavior? Well, initially it's 20, and then at time 5, so U of t minus 5, we're going to go to 10. So we're going to multiply U of t minus 5 times minus 10, because that will have the net effect that after time 5, we're at 10. So that's our in. What's our out? Well, 10 gallons per minute goes out of 40 gallons. So that's 1/4 of everything goes out. So that includes 1/4 of the salt. So minus 1/4 x. Okay, so our differential equation is x prime plus 1/4 x is equal to 20, and all right, this says minus 10 U of t minus 5. So this is our setup. So it is part of our answer, because it does say setup, and we've done that. Now we go to our solve. Okay, so how do we solve? Well, we take Laplace transforms of everything. All right. So we're going to take the Laplace transform of x prime plus 1/4 x. And that's going to be the Laplace transform of 20 minus 10 U of t minus 5. Okay. On a side note, when we take the Laplace transform of x prime, we will need to know what is x of 0. So initially, we're pure water. Pure water, no salt. So x of 0 equals 0. All right. So the Laplace transform, well, we'll pull this apart, of x prime, 1/4 the Laplace transform of x, Laplace transform of 20, minus Laplace transform 10 U of t minus 5. Okay, so here we go. Laplace transform of x prime, it's on our chart, s, f of s, minus f0. Well, x of 0 is 0, so we're left with s capital X. 1/4, Laplace transform of little x is capital X. Laplace transform of 20, can pull the 20 out. We're left with a 1 over s. And then for U of t minus a, we actually have just that. That's on our sheet. And here, so the 10 is a constant, so we can just use our sheet. So this is minus 10 e to the minus 5s over s. Okay, so not too bad as far as differential equations go. We would do the following, say, well, look, I can factor an x out and then divide. So let's just do that in one step. So x is equal to 20, 1 over s times s plus 1/4, minus 10, 1 over s, s plus 1/4, e to the minus 5s. Okay. Well, the nice thing here is it's the same partial fractions that we have to solve. So let's solve it. So we have 1 over s, s plus 1/4, a over s, b over s plus 1/4. 1 is equal to a times s plus 1/4 plus b times s. What's the good choice? 0. S equals 0. 1 equals 1/4 a equals 4. What's another good choice? -1/4. 1 is equal to 0a, and then minus 1/4 times b. b is -4. So, updating, we have the following. We have that x, we have the 20 times 4 over s, because a is 4, minus 4 over s plus 1/4. Then subtract 10, 4 over s, subtract 4 over s plus 1/4, e to the minus 5s. Okay, we're rounding the corner. What happens? So we have our solution x of t, which is the inverse Laplace of capital X. Well, 20 times 4 would give us 80. And then we have 1 over s. We know how to handle 1 over s. Inverse Laplace of 1 over s is 1. So that's the first piece. And then we have minus 80. And we have the inverse Laplace of 1 over s plus the 4th. Well, that's an exponential function. S plus the 4th is s minus the 4th. So that's minus 80 e to the minus 1/4 t. So that's our initial piece. Then subtract 10. And now we do the same thing. And the only thing here, it's the same thing we're working with, but there's this e to the minus 5s. So what's going to happen is, well, we have to shift. So this 4s would normally become 4, but we have to shift 4. Well, it turns out when you shift a constant, it's still the same constant. Then you have, again, 4. S plus the 4th would normally be e to the minus the 4th t. So we now have e to the minus the 4th t minus 5. We're shifting by 5. So this is our f of t minus a. And the last thing we have to add is u of t minus a. So u of t minus 5. So if we write that a little bit better, this becomes 80, 1 minus e to the minus a 4th t. And here we can pull out a 4. So subtract 40, 1 minus e to the minus 1/4 t minus 5, u of t minus 5. All right. Any questions? Okay, on to number 7. A spring is set up with mass m equals 1 and spring constant k equals 4 with no damper. Initially, the spring is in its resting position. Ah, great. Initial conditions are nice. Zeros. For time from 0 to 5, an external force of plus 6 acts on the spring. And at time t equals 8, the system is hit with a pulse, struck with a hammer, with a force of plus 3. No other external forces occur. Set up and solve, using Laplace transform, a differential equation for the motion of the spring. All right, where do we begin? Well, the good news is we don't have any damper, because there is no damper. So our spring looks like mx double prime plus kx equals the external force. So we plug in what we know. We know m is 1. We know k is 4. So x double prime plus 4x. The next thing is we say, okay, what's happening? So there's an external force that only goes from time 0 to 5. So between 0 and 5, there's something acting, and then at time 5, it turns off. Okay, so is this a U or a delta? It's a U. So what we have is we have 6, because that's initially what we have, and then at time 5, we turn it off. So minus 6 u of t minus 5. So this has the effect, it's 6 until time 5, then it's 0. At time t equals 8, the system is hit with a pulse, a force of plus 3. What is that going to do? That's the delta. So it's an instantaneous action, just a one-time bam. So plus 3 delta. And at time 8, t minus 8. And now we have the setup. So the setup was pretty quick. Now we have to solve. Solve using Laplace transforms. Okay, so when we're solving something using Laplace transforms, we take the Laplace of both sides. X double prime plus 4x. Well, that's the Laplace of 6 minus 6 u of t minus 5 plus 3 delta t minus 8. Okay, so the nice thing is these are pretty simple pieces, like x double prime, because x of 0 and x prime of 0 are both 0. This will give us x squared, sorry, not x squared, s squared capital X. So that's x double prime, plus 4 capital X, that's our 4x. 6, we know how to handle constants, so that'll become 6 over s. We know how to handle the unit step function. It's part of our answer here. So we get a minus 6 over s e to the minus 5s. And we know how to handle the delta function, because that's on here as well. And it's right here, delta t minus a. So plus 3, because we have the constant, e to the minus 8s. All right. So there we have our pieces, all laid out for us. Again, you can factor an x out, divide. So we'll have x, capital X, is equal to 6 over s times s squared plus 4 minus 6 over s times s squared plus 4 e to the minus 5s plus 3 over s squared plus 4 e to the minus 8s. All right. What comes next? Yeah, we have to do partial fractions. Now the nice thing is, we don't need to do partial fractions here. The 3 over s squared plus 4. Nothing needs to happen there. And the other nice thing is, we have to do 6 over s times s squared plus 4. We have to do it twice, but it's the same thing. So we can cut our cost in half. So 6 over s times s squared plus 4. That needs to be equal to something over s plus bs plus c over s squared plus 4. Clear out your denominator. 6 is equal to a times s squared plus 4 plus bs plus c times s. Any good choices? 0 is a great choice. At s equals 0, we get that 6 is equal to 4a. So that says a is equal to 3/2. Are there any other good choices? No, not really. We could go and try complex again, but I don't know if we're in the mood for that. It's getting late. Our minds are starting to slow down. So, well, maybe yours aren't. I have an older mind here. So what I'll do is I'm just going to do, after you use up the good choices, if there's only one left, just pick a number, any number. If there's 2 left, okay, maybe pick 2 numbers. But the other thing you can do is just expand and say, let's look at coefficients. So we know what a is. So we have that 6 is equal to 3/2 times s squared plus 4 times 3/2. Well, 4 times 3/2 is 6 plus b times s squared plus c times s. Of course, the 6's cancel. So we get that 0 is equal to 3/2 plus b times s squared plus c times s. What's our conclusion? Well, what needs to be the coefficient for s if both sides match? On the left-hand side, the coefficient is 0. So that says that we need c to be 0. Coefficient for s squared. Well, left hand, it's 0. Right hand, it's 3/2 plus b. So b should be negative 3/2. So we've solved for our coefficients. So we can now update. So here we go. We know that x is equal to, we have our 3/2 times 1 over s minus 3/2 s over s squared plus 4. So this is the first part. Minus, and again we'll have the same thing, 3/2 1 over s minus 3/2 s over s squared plus 4 e to the minus 5s. And on the end we have our 3 over s squared plus 4. Well, you know, in anticipation, I'm going to rewrite that as 3/2 2 over s squared plus 4 e to the minus 8s. Now you might say, do you just like the number 3/2, Steve? Well, not just that. What do I want? 2 over s squared plus 4 matches the sign. And I saw the sign, and it opened up my eyes when I saw that sign. So I just wanted to make sure it lined up. That's why I did that. All right. So we're ready. Take the inverse Laplace to find our answer, x of t. And what do? Well, we have our 3/2, and the inverse Laplace of 1 over s is 1, so it's just 3/2. S over s squared plus 4 is on our chart. That would be the cosine of 2t. So minus 3/2 cosine 2t. Okay, so that's our first piece. Subtract. Now the next thing is going to be the same function shifted. So this e to the minus 5s says there's a shift. So I see, okay, everywhere I see a t becomes t minus 5. So 3/2 minus 3/2 cosine 2t minus 5. That's the shift. And then I have to add that on-off function, u of t minus 5. So the last part, we'll add a 3/2. And what do we have? Well, 2 over s squared plus 4 is normally sine of 2t. But it's sine of 2t where t has been shifted by 8. So it would be sine of 2t shifted by 8, t minus 8, then a u of t minus 8. And that's the answer. One thing to note, deltas in our problems become used in our answers. Yes? Explain which part? So u versus delta. So u is on off. So anytime you're changing behavior for any sustained period, that's a u. A delta is a whack. It's not sustained. It happens at one instant in time. And so you ask yourself, if it's over a period of time, that's u. If it's at one moment in time, that's delta. Okay, now that we finished the first part, on to the second part. Now, before, if we had said, what's going to be your favorite part on the exam, the series or the Laplace transforms, most people say, not series. But after they take the exam, they're like, I like series. Series are good. Give us more series problems. Okay, so number 8. Given that y is equal to the sum ck x to k is a solution to y double prime plus 2xy prime minus y is equal to 1 over 1 minus x, then write c2, c3, c4 in terms of c0 and c1. So in essence, what you can think of what's happening here is normally c0 and c1 would be your initial conditions, your y of 0, y prime of 0. But we're not going to give you initial conditions. However, everything can come back to those initial conditions. So our goal is rewrite our coefficients in terms of the first ones. Now, I have a basic mantra. There's sort of two ways you can approach these types of problems. One is find the recurrence relation and use that. And the other one is be fast and get the same answer. I prefer the be fast. That's just my default. So how does the be fast method work? It says, look, I just need a couple pieces at the start. So I'm just going to focus my energy at the start. How much do I need? I need 3 pieces. So that says I just need to go far enough so that I get 3 pieces of information. So here's my idea. I shouldn't claim it as my idea. People have been doing this for a very long time. But here's the way I like to approach it. Say, okay, let's say that y, it's c0, c1x, c2x squared, c3x cubed, and c4x to the fourth. And then it's other stuff. Do I care about this other stuff? No. I don't need that. I just need to figure out up to c4. Okay, so we're going to need to know what y prime is. Well, all right, so we take our first derivative. No worries. And whoops. So c1, 2c2x, 3c3x squared, 4c4x cubed. Y double prime would be 2c2, 6c3x, 12c4x squared, and other stuff. Now we're going to just plug in. We're going to take y double prime, 2xy prime minus y. So we have y double prime. I'll just start here, 2xy prime minus y. Well, that's equal to the 2c2, 6-3cx, 12c4x squared, dot, dot, dot. So there's our y double prime. Plus 2xy prime. So I'm going to multiply here by 2x. Now, I'm just going to point out here, notice how I stop at x squared? I don't need to go anything past x squared again. So 2xy prime would be 2c1x, because I'm multiplying here by 2x, plus 4c2x squared, and then higher order terms. But I don't need the higher order terms. You can add more if you like. Don't feel like you have to be as efficient as possible. But I just want to say, look, I'm only going to write what I need. Since I stopped at x squared, everything else should stop at x squared as well. Minus y, so minus c0, c1x, c2x squared. And of course, other stuff. Okay, when we gather our constants. We have our 2c2. There's no constant here. Minus c0. We gather our x's. There's a 6c3. There's a 2c1. There's a minus c1. We gather our x squareds. 12c4. Our 4c2. And a minus c2. And there's other terms. All right, so I've essentially said, look, I know what y looks like, and I need 3 pieces of information, so I ultimately just need to grab enough so I can grab off the constant x at x squared. That's going to be my first 3 pieces of information. I have put a lot of energy into that left-hand side. I've got to put a little bit of energy into this right-hand side, but not too much, just a little bit, just enough. 1 over 1 minus x. And you might think that we're done with the equation sheet. But notice there's a little bit about series in our equation sheet. 1 over 1 minus something and e to the something. So if one of those shows up, we know how to handle it. So 1 over 1 minus x actually turns out to be really nice. It's just here, this is the sum of x to the k. So it's 1 plus x squared plus x cubed and so forth. But we already know we only need the first few pieces. So this is 1 plus x squared dot dot dot. And now the matching game begins. 2c2 minus c0 is our constant. That has to match up with our constant. So 2c2 minus c0 is equal to 1. Now, remember our goal. It says write c2, c3, and c4 in terms of c0 and c1. So it's okay to have my pieces on the right-hand side involve c0. So I would say, okay, in that case, that would tell me that 2c2 is 1 plus c0, or c2 is 1/2 plus 1/2 c0. And this is part of my answer. c2 is in terms of c0 and c1. Well, now we continue the game. Say, look, we have our coefficient for x. That has to match our coefficient for x, which in this case is a 1. So we get that 6c3, 2c1 minus c1 is minus c1, is equal to 1. Okay, 6 times c3 is 1 plus c1. So c3 is 1 over 6. Is it plus c1? It is plus C1. 1 over 6 minus, very thick minus sign, 1 over 6 C1. And now we come to our last, but not least, piece. So we have our coefficient for x squared, has to match coefficient for x squared. So 12C4, 4 minus 1 makes 3C2, has to equal 1. Well, that's nice. We can do the same thing, right? 12C4 is equal to 1 minus 3C2, but we have a problem. That's not C0 and C1. So how do we replace this C2? We use what we know. So we say, oh, okay, so this is 1 minus 3 times 1/2 plus 1/2 C0. So in other words, we come back to what we've already solved. So 1 minus 3/2 is minus 1/2 minus 3/2 C0. But remember, this is 12C4. So that says C4 would be minus 1 over 24. Then the next one, 3 over 24, which is 1 over 8, C0. And now we have exactly what we want. C2, C3, C4 in terms of C0, C1. Okay.
I'm still a bit confused why you should just simplify the equation like that 2C2 minus C0 plus 6C3 and everything. Why you get to set that, why do you get to set that equal to the summation part?
Why this is equal to that?
Yeah.
Well, because this left-hand side is what you get when you plug in the y equals this into this expression and gather your constant x and x squared. And then the right-hand side is the 1 over 1 minus x. So essentially, I'm comparing a polynomial to a polynomial. And then I'm just making sure coefficients line up. All right, are we ready for number 9? I think we're ready. We're more than ready. We were ready an hour ago. Number 9. Given that y equals the sum n equals 0 to infinity cn x to the n is a solution to y prime plus 2e to the xy equals 1 plus x squared with y of 0 equal 1, then determine C0, C1, C2, C3. So this isn't the first part of the course where we try to solve this by doing some kind of integrating factor, because that probably would be a little hopeless. We're just going to work it out. Now again, we have two choices. We can look for the recurrence relationship, find that, and then use it, or we can just say, look, I only need to know what I need to know. Now a few things are a freebie. When they give you initial conditions, y of 0 equals 1, that's C0 equals 1. You can see that by saying, well, plug in 0. What happens when you plug in 0 into the polynomial is you get the constant term. The constant term is C0. Now here we only had a condition for y of 0. If you gave us y prime is 0, y prime is 0 is C1. All right, but again, we've already found one of the 4 terms, and we've hardly broken a sweat. 3 terms left to go. All right. So again, unless you have a strong reason to find the recurrence relationship, it's usually faster and easier to say, I'll just look at what I need. And so in our case, we say, all right, what are we going to need? Well, we know what our y0 is C0, so I'll just write this as 1, plus we have our C1x, C2x squared, C3x cubed, and that's all we need. Everything else we don't need to worry about. Okay, y prime Well, that's C1 plus 2C2x plus 3C3x squared. So we now have the following. We're going to plug these pieces in to y prime and to y. And so we have y prime, that's our C1 plus 2C2x plus 3C3x squared, other stuff, plus, now we have 2e to the x. How do we handle 2e to the x? Well, the thing is, everything needs to be polynomial. It's one of the big punchlines of Calc 2. The end of Calc 2 says everything's a polynomial. And we're like, oh, that's awesome. We're just coming back to that. Everything old is new again. They're saying, great, I need to make 2e to the x look like a polynomial, which is what this does for us. We use our series for e to the x. So 2e to the x, if you recall, e to the x is 1 plus x plus 1/2 x squared plus dot, dot, dot. That's just the expansion for e to the x. So 2e to the x, you just double that. So that's 2 plus 2x plus x squared times that by y, which is 1 c1x c2x squared and dot, dot, dot. We can stop at the square term because we only need to get to the square term. The x cubed would give us higher order stuff. That has to all equal 1 plus x squared. All right. Well, what comes next? We're going to do a little bit of work in this multiplication. When you're multiplying two polynomials, how do you do that? Well, you FOIL. Well, wait, what does foiling mean when there's infinitely many pieces? Foiling says every possible way from the first, every possible way from the second. And so you just work up by your powers. So for your constant terms, the only way you can get constants are constant times constants. So that would be 2 times 1, which is 2. If I want to get x's, I can take constant times x or x times constant. Notice how my fingers move in opposite directions. So 2c1 plus 2. So plus 2c1 plus 2x. For x squared, constant x squared, xx, x squared constant. Again, they move opposite. So plus 2c2 plus 2c1 plus 1 x squared, and then everything else. Now, put it all together. On the left-hand side, we have our constants, c1 plus 2. Our coefficient for x, 2c2 plus 2c1 plus 2. All right, coefficients for x. Our coefficient for x squared, 3c3, and then 2c2 plus 2c1 plus 1 equals 1 plus x squared. Oh, and I should have put in here plus dot, dot, dot. The plus dot, dot, dot says there's other stuff. Don't worry about it. We don't need to look at it. Okay, so recapping where we are at, what we have done. We said, look, I know I have a big infinite polynomial. That's my series. I'm just grabbing the part the part at the start. I can say words that rhyme. The part at the start. The flagon with the dragon. And the brew that is true. Okay, anyways. The part at the start. We're just grabbing that, plugging it in, and saying, what does it look like at the start? After you do all that, we're ready to compare. I see a question? Ah, yes, there is an x squared here. X squared plus dot, dot, dot. There's a lot happening there. Okay, so here we go. Constants on both sides have to match. C1 plus 2 has to equal 1. What does that tell us about C1? -1. Okay, good, because we already found C0. So now we're halfway. We found C1. All right. Now, let's go to our x term. Our x term has to match. But wait, what is the x term over here? 0. So we get that 2C2 plus 2C1 plus 2 equals 0. But wait, we already know things. That's 2C2. C1 is -1, which is -2 plus 2 equals 0. So what is C2? C2 is 0. And another one bites the dust. Our last piece. So we have 3C3 plus 2C2. Well, we know C2 is 0. So, okay, plus 0 plus 2C1. We know C1 is -1, so that's -2 plus 1 has to equal, coefficient on the other side is 1. Well, the 1's cancel. We get that 3C3 has to equal 2. So C3 is 2/3. And now we found all our pieces. So we found our C0, C1, C2, C3, which means that our solution, we don't need to write this, but we could, our solution looks like the following. Y is 1, our C0, minus x, 0x squared, 2/3 x cubed, plus other stuff. And that's sort of a condensed way to put them all together. All right, which brings us to number 10, our final problem. Wonderful. We've been waiting so long. Okay, number 10. Given that y, which is this sum, is a solution to y double prime plus 2 minus x squared y prime plus xy equals 0, with y of 0 equals 4, y prime of 0 equals 2, then find a recurrence relationship for the coefficients, and also find C0, C1, C2, C3. What approach should we use on this problem? Well, we kind of don't have a choice. It tells us. So if it asks us for a recurrence relationship, we're going to have to find one. And since you've been so patient, I will say, very likely, among your two problems, one of them will probably have the phrase recurrence relation, and one of them will not. Take that as you will. So you want to make sure you can do problems with recurrence relationships, and you want to be comfortable doing them without. Now, you don't have, you can always do recurrence relationships, but it's just more work. And you only get 75 minutes. You don't want to take too much time, because you want to take time to admire your test at the end. Say, oh, what a beautiful test I've made. Okay, so for recurrent relationships, we start with our y, and for some reason we put L's here. So 0 to infinity, c sub L, x to the L. We're going to go up to second derivative, so I like to put them all right away as reference. So y prime, 0 to infinity of L c sub L, x to the L minus 1. Y double prime, sum 0 to infinity L minus 1, c sub L, x to the L minus 2. So those are our pieces, and we now put them in. So we have our y double prime, this sum, L equals 0 to infinity, L minus 1, CL, x to the L minus 2. This 2 minus x squared y prime. Now, I would encourage you to split this as 2y minus x squared y prime, because you're going to do something slightly differently with each piece. So I'm going to, 2y prime minus x squared y prime. So plus 2y prime, L equals 0 to infinity, L c sub L, x to the L minus 1, minus x squared, sum L equals 0 to infinity, L c sub L, x to the L minus 1, plus x times our y, L equals 0 to infinity, c sub L, x to the L. All of this equals 0. Okay, so what's going to happen here? Well, we're going to put pieces in. There's powers of x are going to come in. So we're going to multiply an x on that last term, an x squared on this penultimate term. And okay, we'll go ahead and carry that out. I guess we're doing this one in a little bit slow motion, but it's just we want to make sure we're comfortable with whatever might happen. So we have our first term. We can even put the 2's inside if we wanted to. Sum L equals 0 to infinity, 2 L c sub L, x to the L minus 1, minus the sum L equals 0 to infinity, L c sub L, x to the L plus 1, right? Because it's plus 2 coming in, so L minus 1 plus 2 is L plus 1, plus the sum 0 to infinity, c sub L, x to the L plus 1, equals 0. All right, now when you're finding recurrence relationships, you have to basically go through a procedure. You put your sum in for all these pieces. Next thing is make sure you get the powers of x to agree. Once you get the powers of x to agree, figure out where to start, maybe pulling off some terms, and then squish it together and life is good. Okay, so we've done the part where we put in, well, we know what y looks like, substitute it in. Now we do the part that says, let's make our powers of x agree. So we go through and say, okay, here I have a L minus 2, so I'm going to let k equal L minus 2. Here I have an L minus 1, okay, k equals L minus 1. Here I have an L plus 1. All right, I'll let k equal L plus 1. And here's another L plus 1, so again, I'll let k equal L plus 1. So I can just go through and figure out how do I need to change my names. And then we have to be a little bit careful. And k equals L minus 2 is the same as saying L equals k plus 2. Here, we'll do the similar thing going all the way down. We can rewrite all these pieces. So our first sum becomes what? Well, if L equals 0, k is minus 2. That sounds terrible, but wait. Notice this L times L minus 1. It's actually 0 for the first value at 0, and it's 0 for the second value, which is, plug in 1. So I can change where I start, move it to 2, because the first two terms are 0 automatically. Since the first two terms are 0 automatically, I can just say, look, don't start at 0, start later. You haven't lost anything. So if you do that, you say, oh, okay, this is now the sum from k equals 0 to infinity of k plus 2 times k plus 1 c sub k plus 2 x to the k. Now, on the next term, we can do the same thing. Notice here, if I plug in 0, I get 0. So I'll just do a shift to 1, because I'd rather have my sum start at 0 than start at negative 1. So this becomes the sum, k equals 0 to infinity of 2 k plus 1 c sub k plus 1 x to the k. All right. Now, we're halfway through. The next ones aren't so bad. when you plug in L equals 0, we get K equals 1. So we say, okay, so we won't do anything tricky. We'll just see what happens. We get K equals 1 to infinity of K minus 1, right, because L is K minus 1, C sub K minus 1, x to the K. And our last piece, similar, K equals 1 to infinity, C sub K minus 1, x to the K. Okay, so we've shifted. Any questions? Yes?
Why is the second one in the blue after you distribute? The one next to that, why is the L not
Why is this one?
No, why is the other one not 1 as well?
Why is this one not 1 as well?
Yeah, why is that one?
Well, we could have. Oh, sure, we could have. Now, if we made this one 1, which we absolutely can, what would be our new starting point? So if L equals 1 is our start, when L equals 1, K would be 2. And so I didn't want to shift that one because that would push my starts, the common start, further back. I want to get the common starts as close as possible. And so that's why I didn't do it. I didn't move this subscript, even though I could have. I could have changed it starting at 1, but then my common start wouldn't be until later. We haven't gone to the common start yet, but that's why that happened. All right, well, the issue is the starts aren't at the same place. So we've set up, see, this could have been at -2, -2. This could have been at 1 or 2, but in some sense, this is as close as you can get the starts to each other. So I say, well, we're going to pull off the first terms. So the 0 term here, the 0 term here, then everything else will be the 1 term. So for the 0 term, we're going to get 2 times 1 times C2. So that would give us 2 C2. Here, what do we have? We'll have 2 times 1 times C1. So plus 2C1. So I've pulled off the 0 terms. Everything else starts at 1. So I can now put it all together into one sum starting at 1. And I grab my coefficients. So we have K plus 2, K plus 1, C sub K plus 2, plus 2 times K plus 1, C sub K plus 1, minus K minus 1, C sub K minus 1, plus C sub K minus 1, x to the K. So we pulled off some starts so that everything else could start at 1. Then once everything started at 1, just smooshed it all together. And now our great aha for the recurrence relationship is going to come from the sum. It's going to come from here. These are our coefficients. But looking at what happens to our coefficients on the right-hand side, what do these need to be? These all have to be 0. So we get K plus 2 times K plus 1, CK plus 2, plus 2 times K plus 1, CK plus 1. If we wanted to, we can even combine these together. So notice these both have a CK minus 1, so there's minus times K minus 1 and a plus 1. So you could write this as 2 minus K, CK minus 1, all has to equal 0. So this is our desired recurrence relation. And this is starting at K greater than or equal to 1. So from 1 on. Okay, so we found it. Whew. Nice. Are we done? No? Darn it. I'd really like to be done. Well, we can finish up the rest of it. We have to find 4 coefficients. Is C0 a freebie? Yes. It's our initial condition for y of 0. Is C1 a freebie? Yes. It's our y prime is 0. How do we get C2? Well, notice our constant term has to be 0. So we set this equal to 0. What does this tell us about the relationship between C2 and C1? So C2 has to equal negative C1, and we know C1 is 2. So negative 2. So now we found C0, C1, initial condition, C2, our constant terms. That leaves us with just one more to go, C3, and then we can call it a night. Where do we get the last piece from? The recurrence relationship that we worked so hard for. We should do at least one thing with it, and here's our one thing. We plug in 1. Okay, so 3 times 2, 6, C3. 1 plus 1 is 2. 2 times 2 would be 4. So plus 4. And then that would be C2. 2 minus 1 is 1. So plus C0 equals 0. But we know C0. And we know C2. So this becomes 6C3 minus C0. Become minus 4. 4C2 is, well, it's minus 8. Move it across, it's plus 8. So you get 6C3 is equal to 4. So that tells us that C3 is 4 over 6, or 2 over 3. And we found our last piece. Done. Done. Oh. All right.